Patrick said he would.
But it's in the common room.
Well, he said he done in 5 minutes, like 10 minutes ago, 15 minutes ago.
Yeah, it's a 5 minutes. So, we have this one-dimensional eigenvalue problem. And the basic setup is this: when B is maybe first, right? Is, let's say, B0 when X is less than A and 0. When X is less than A. So our potential is something like that. So I have B0 here, and then here I have 0 level. So what we do is we just want to see, you guys should get some color here so that the next picture will be. So we'll look for the energy AE here, and my E is going to be between B0 and 0. And we know that here my solutions are oscillating. Maybe I should continue being continuous. And here I have exponential. And that's because we can easily solve that. So this is called the allowed region, which is we're going to call 1, and then these are called the forbidden. So you can easily write the solution right here. Your equation is going to be will be EF. So you will have oscillating cosine root EF and sine root EF. And on the other side, you will have E minus V0, which is going to be negative half. And if you're looking for alpha ones, you're gonna have solutions like V0 minus E. And so, right. And so we talk about inside the allowed region and outside the allowed region, which is forbidden region. And to make it continuous, like a strong solutions, we say that it's continuously differentiable, and then match these values at A and negative A, and you can find the allowed energy. So this is the basic picture, and we wanna a little bit complicated version is gonna be something like this. So I'm gonna have some sort of a valve here, and I'll expect my potential to stabilize at infinity. And I look at the energy somewhere here. So basically this is my V0. I want E to be greater than V0, and this will be less than infinity. As X goes to infinity. So if I do the same understanding, and if this is Vx, so my question is going to turn something like. And hence again, I will expect oscillation here and exponential decay here in the same way. Maybe I shouldn't really connect here yet. So let's leave it. So we again have the allowed region, and now we will again have a forbidden region. In the allowed region, we will have oscillation, and outside we'll have the exponential decay. Here, so here where the WKB actually comes across. In this problem, we can straight write everything, but here we cannot, so that's why we're gonna actually approximate. So the solutions we can approximate the solution with W. How does that work? Okay, raise here. So this information is stolen from Wilhelm's paper. And so suppose that we have problem like that. So this is gonna be like BXF if we compare with that problem. And let's suppose I be an interval such that QX is not zero.
You mean Q times F?
Oh, yes. QX is not zero in I. And we define W from I to J such that 2x divided by W prime x squared will be the sine of 2x. So it's either plus and minus, like here, we already assume it's not zero. And this is something that I'm gonna call V0W. Then if you do this change of variable, to the 1/2 fx, then our problem one turns to this equation.
So if do you mean G is G of W? Or what?
Yes. Then our equation turns to an equation of W, which is gonna be U F plus V W of G. Now, this is depending on, of course, the sign. I meant to put here Q0, sorry. So this Q0 is gonna be either plus and minus 1, so this is gonna tell us actually what we are linear. And then here, we expect this guy to be small in some sense, and that W is also calculated. And it is calculated like this. Or y body. So what you want is, once this part is, let's say, the integral in terms of x in I, in terms of W in J, if the integral x in I, let me say, is finite, then this tells you that you can actually approximate your solutions. And that's gonna give us the WKB part, the leading part. I wish I hadn't raised my picture, but so then.
You're changing variable, like, is it a function of W or X?
This one is function of W.
You're continuing with
This is W.
Even the derivative
Huh?
even the derivative is in terms of W.
Can we understand that basically you reparameterize by arcane, or in other words, that you have some form of Riemannian Laplacian in 1D, if you were to divide by Q of X, and then of course in 1D there is no geometry, so you can always make it so that the max is 1, and so now you're really Like just this reparametrization of the basis of R,
Mm.
we've made it into essentially a flat derivative. Or just reparametrization by R.
Yeah, I think it sounds like,
Yeah, so this is amazing. This is the Leo drink transform from 1820. So it's 100 years older than W3D, which is a special case of it. And this is much more powerful than W3D.
But WKD is multi-dimensional.
Well, April will tell you.
But I think, or I don't know, the way I understand it is really just you're writing this as a fashion, a Riemannian fashion, and then using the fact that in one there is no geometry, or that there is nothing. So we can always reparameterize. So then I think it's not so fantastic that you would, I mean, it's great that you get the idea to do it, but after the fact, it's, you can see that maybe there was a way to do it.
So, maybe what you're saying is that okay, you divide the equation up there in the first line by Q, and then you view it as a change of metric, because one of the Q is then a factor from the past, and that's exactly the rescaling you need to make it the constant. Exactly.
so it's kind of in the integral, you're doing change of variable in the norm. Yeah.
But then
Yeah.
you really use your 1D fact.
You know, that's interesting because actually that's what I did in one of my paper before, but I did not really connect this to that while just looking at it. So, but now, thank you.
And one more comment, why do we change both independent and dependent variables? So the reason we multiply by the root of W prime is so that we do not get a first derivative of W. So that we get only second derivative of 0.
Yeah.
That's the reason.
Yes, that's the thing that I thought.
The root W prime sits there, so that we don't get a G prime.
I can also understand it as the Jacobian, because the L2 from your original idea, and the L2 is the mean.
That's much better than you see.
So if this is, as we discussed, small in some sense, then we can actually approximate our F. If depending on Q0, of course, either Q0 is not greater than 1. So if it is greater than 0, then it will be like 4. Of course, that 0 is some element in R. Okay. So this argument works, of course, you see, because we are turning Q0 to 1. Either you are on the right and the left. So this was our picture. And we had this stabilizing part. Now we had this. So we can approximate here, here, and then here. So what happens in the continuous part? It depends actually, of course, how Qx is going to 0, how fast it's going to 0. So we assume like Qx going like to 0 in a linear way. Then we actually obtain, when Qx is kind of linear, then we obtain the area equation, which is not G, but let me use square. That's plus and minus, but let's actually take a -1 so that we know actually how to solve this. So if you approximate to 0 in x squared, Tom told me that it's actually harder, so I don't really know.
with the even, or exclude.
Yeah, but this,
Depends on the
Yeah.
order of contact.
yeah,
That way, the easiest way is to.
but it's linear,
But
yeah,
in your picture, look, you can. have
yeah, it's like
At the
linear,
potential maximum and minimum.
yes.
That's called top of the variance schedule. Delicate thing. It's a.
And we know actually the solution of this area equation, which are in terms of AI and BI, and this is what we have. As x goes to infinity, we have this AIX is approximately 1/(x⁴), and e to the negative 2/3, x⁴. Sorry, 2/3. This is right, that's right. And the other solution,
Wait, so we have to take the minus x then?
yeah, you were right, but I just didn't wanna,
No, but for this to be correct. I'm confused.
so
you-
this, if you think here,
You say a double prime for x at the zero. Then if x is positive.
okay, let me,
minus,
yeah.
Then you get that.
Yeah,
It's x is to plus infinity.
yeah, then I would, yeah, in that case, I would change just this is a negative. That's- so this is what happens as x goes to infinity, and I also have actually some approximation when x goes to. So why I wrote these approximation, because I want to tell you actually like this WKB gives this exact, it predicts exact this precisely like this, this behavior. If you just, so what do we have? So x, if I take like x is positive, and if I consider, so if my x is positive, my Q0 is negative, right? So this one exactly estimates, predicts this behavior in a very precise way.
Just Ebru.
Uh-huh,
So there, I see that AI is the by function at plus infinity. So among all the solutions, the only one that is going to be paid at plus infinity. But then BI, how was it?
I mean,
So
you are right, so we
just-
need to take the L2 one, that's what you are saying, say it again, maybe I missed the
No,
question.
I understand how AI is more or less uniquely defined as the only one that
The
detects
case,
zero.
uh-huh,
But BI seems like if you were to replace BI by BI plus 2AI, you'd have the same property. Basically the same property.
Yeah.
So, but one has been picked.
yes,
Is
that's
it
the,
because it's the sine and cosine, or is there another, what is the significance of BI? Do you know?
to be honest, this is what I would think. Because we're looking for the eigenvalue problem, that's what I would think, I just take the one that's decaying at infinity, but I don't really
But,
know.
I mean, somehow somebody decided to call BI.
Oh,
They did not pick BI plus AI, which has
Oh.
the same property. So you want to have like a different of phase by I.
I don't know
Yeah,
really.
it's because of the cosine, as you said.
I mean, I only took this from someone,
And it's just, I mean, just need to give them a name, but I was,
yeah,
I
curious,
always understand why AI is defined, but BI, it seems like.
I don't, yeah.
Just a representative of the
I don't, yeah. Okay, so, what we said is. So, yeah, exactly, if you take like a X, if you just apply this formula, right, in which what we had, I just erased here. But this was the part, right, we need 2x over W x squared to be 1 in there, if we think, for example, as x goes to infinity. And that would tell us that W prime x it has to be x to the 1/2. I don't really know why I went there. Because this was actually, so, oh yeah, I still need to show that actually this part is somehow close, but somehow small, right? Okay. Let me start where I was here. Okay, so if you look at here, right, so my double prime is gonna be 1/2 x to the 1/2, and my triple x will be -1/4 x to the -3/2. So in fact, my W is gonna look like, one of them is gonna be -3/4. So if I consider W prime divided by 4 times this one, so it's gonna be, actually we can say that this is gonna look like almost 1 over x to the, let me think about it again. So the prime 4 is x squared, 1/2, x to the 5 over 2. Is it? Yes. And if I want to write it actually in terms of W, you see. Let's have something like that, and this will be 1 over W1 plus what? I subtract 1, I'll have 3/3. Something like that. And which is actually integrable in any part. Let's say 1 to infinity. So that's why actually this is gonna be a good approximation. And that's exactly is gonna give us something like this. By just taking 2x equal x. I take x, and WKB is gonna approximate my f as 1 over x to the 1/4. I don't know if I need to, right? But integral, let's say 1 to x to the 1/2 e x minus integrate.
Wait, so you probably integrate x dx.
Yeah. So I will have exactly the same. X to the or minus. But it's going to just give us a constant. So I want to say something more about that. No. So now, how do we generalize this? That's actually where the Agmon metric is coming into surface. So this is one-dimensional version of that. And this is how we put everything. So how do we generalize WKB to higher dimension. So in order to generalize, we actually define an inner product that's defined as dx minus epsilon plus xc, and this is just an Euclidean inner product. And then we take the induced length formula from this inner product. Huh? Oh, yeah. This I said Euclidean, so this is the Agmon inner product, and this is just the regular one. Maybe I shouldn't even put just the regular inner product.
And so you don't add the two, you multiply the.
Oh no, this is plus. I'm gonna define it in a bit. Yeah. So this is defined as gx plus is a minimum 0 or gx. So this is the inner product. Oh, yes, it's yeah, of course, because clearly it can be 0, even though they're not.
But so just if you're going to try the same thing, then at least in my analogy, now you look for a metric that is conformal to the Euclidean one, and then try to use also to conjugate the Laplacian to the flat Laplacian.
Say it again.
So if I think of it as the analog to higher dimension of arc length, now your metric is, you choose a metric that is conformal to the Euclidean metric. And then the Laplacian is going to go to the conformal Laplacian corresponding to the symmetric. And this is how you manage to get to a new
Yeah. I see. So our length formula will be 0 to 1. And we write that 17 minus 1. P bar gamma is a path from V1 to R.
It's entrance then.
Huh?
It's entrance.
It's what?
Entrance. Squirrel.
Oh, sorry. Yes, maybe I should. Yeah, you're right. Then we write. I'm going to get rid of the increment of all gammas. Into 1. For I'm sorry, such that gamma 1 is x, gamma 2 is y. And of course, maybe I should also say gamma is so
We want to integrate the tangent vector.
I have actually not here.
You mean gamma 0, like gamma 1?
Oh, yeah, I don't. Okay, so there are some properties of this symmetric. And one of them is, it holds the triangle equality. So. And therefore. It's local ellipses. So in other words, if you take a straight line from y prime, then it's y minus x y prime by just using this triangle inequality will be exactly like 0 to 1. If you just actually I don't think I really need to read down the tweet. So y minus y prime dt. And because we are local, we can bound this by something that depends on our domain. So that will be some bound y minus y prime, where this depends on, maybe I should r my, if I am in kind of domain, so on. And if I am locally rigid, then that means I am differentiable almost everywhere. And this is actually gonna be important because we will be able to take the derivative and we can actually bound derivative. And that's where the where this expansion is the for.
Just a question. Because so if you were talking about the Riemannian metric, then you want the geodesic, then the geodesic will satisfy analogy. And you get it by looking at the energy, for example, instead of
Yeah.
you have the same properties here as well.
I mean, I don't really know. So basically you are just trying to minimize the energy by the geodesics. That's what you are saying. It's the same thing now.
So the definition of the length is with the norm of the derivative, and then you can define the energy as
Yeah.
the norm squared. And at least in the Riemannian setting, it's the same curves that give the extremizer of the two. And then if you minimize the energy, you also get the parametrization. So it's not just the curve, but the parametrization is easy. And I think it also gives you it feels very similar.
Yeah.
So you would also get an OE for the minimizing curves. Yeah.
You get the second order provided because the V is able to assume this V is continuous singles to infinity, and all of this makes sense. But when
even if it vanishes somewhere, for example.
Oh no, then it's different. Then of course you lose your interest. There is no one. Then you, yeah, if the gamma is not true, then there is no one.
So now we can define the derivative. So I will, have h equals 0. Right. So so I will have H here, and then that will cancel the H, right? So I will have 18. And so this will be the derivative, like here, B. E. X. So this is limit. I think there's, let me write it, limit H goes to 0, limit to. Right, so I will have E X Y plus H minus P X Y. And I'm gonna divide it by H. And if I use this formula, then that's what we found actually by the Y minus E. No, yeah. So let me write it again, but this is gonna be saying that. Maybe. In fact, I should just say it's 0 to Y will be less than Y.
What is?
The derivative, the BP. BP. Okay. So now this will be our theorem that actually, which will be the generalization. Okay, so this time we will have higher dimensional Schrodinger, and then our V will be real and continuous, and it will be regular enough such that the spectrum of H will be a set of R. And so let E be an eigenvalue of H, and the support of A minus Vx plus will be compact, and that's something that we will need actually, is compact. That's the compactness. So here, if now C is the eigenfunction, corresponding eigenfunction corresponding to E, then this is what we will have. We will have this will be bounded for some alpha positive. And in fact, so in fact, this is right, okay, so this will be, let's leave it this way. So let's leave it this way. So we will be able to find an alpha such that this is going to be bounded and alpha will be greater than 0.
And just the thing that you just erased, the point was that you at some point you replace X by 0, and it's that it doesn't. If you fix one point, it doesn't. The derivative.
Yeah. Yeah.
So on 0 plane mode, especially.
Yeah. Just a second, I'm just checking out something to make sure. Yeah, so in fact, like this part can be replaced by as epsilon x, and that is 1 minus epsilon, and so PE x. I just put x, this means 0x actually, so that's why I just put it at 0. And in fact, this is what I needed to define anyway, but instead of this, I'm gonna define something different, because this can be unbounded, and on the way of the proof, we're gonna do some integration by parts, and this unboundedness will not really allow us this integration by parts, so instead I'm gonna define with n.
So, I guess PE is Lipschitz. So the one thing that you want was that you can explicit the constant alpha and replace it by almost 1. What does that value to replace e to the alpha x by e to the epsilon of x? Is the point that you have the constant 1 times PE, or?
Yeah, I mean, this is actually the optimal estimate.
Because of the 1, because otherwise PE
Oh, yeah.
is probably less than the constant times x anyway. So the point is that now you can really get the exact growth.
Yeah. So honestly, there are a couple of results, and this was one of them I saw. Then later I saw this one, and then I said, wow, okay, so this looks better because the proof exactly like established this. But
in the sense that if you were to put 1 plus epsilon PE of x,
yeah, it doesn't.
Infinity.
Yes, exactly. You cannot, like this has to be here. Yeah. It's gonna be very clear actually in a bit why we actually need that next step, like the first step of the proof, it's gonna come direct. Okay. So I'm gonna define this, and this will be minimum of this one for some. And remember, we had this bound on the derivative of PAX. So in fact, we will have the same bound on this guy as well. So if we consider this one, we'll have epsilon n again. So, oh, I only have x already, so I don't have to worry about actually xy time. So what do we have? So this was bounded by v minus epsilon plus times y minus epsilon. So now, where all this epsilon comes will be now clear in the first step of our. So the first step will be this. Huh? I put here a weighted L2 bound, right? So that's.
Says in the question that if you have a potential V that goes to 0, there's convention support for which depending operated in RT, then any function with negative eigenvalue must be declared exponential. you see that from the first example, if we take just from the square well, the optimal rate is potentially zero outside of the wall, and the decay rate has to be e to the root of the negative energy, right? And this is an L2 average state. But this is somewhere that in upward is pointwise. It's exponential. So it's a form of a tolerance. So commutation with an exponential rate.
So what I was doing, sorry. So, okay, we were proving, right? Okay, so this is what I'm gonna show. So I will take 5, which is gonna be supported in the domain such that X minus E will be greater than that. And you see, once we have something like that, this is what we will see. There will be another delta 1, which will be again related to that delta and the epsilon that we have, which that the L2 norm of this one will be less than equal to the inner product of En pi, which minus e to the negative Fn pi. So now that epsilon will be now useful over here. And the reason is because you see, if you look at e to the epsilon n, h minus e to the epsilon n, then you actually will have h minus e plus, and then here you just commute, and you will have e to the epsilon n, and minus a fraction into with negative e to the epsilon n. Well, actually, I should put real part here. That will make things a little easier. And then once we
And the first thing after the equality is H minus E or
E.
H. The next one.
oh e yes. So once you look at this one, it will give you the epsilon n. Actually, the whole thing is gonna give you, because this is also gonna cancel, so let me write this. It's gonna be negative dA epsilon n squared, and then you will have this anti-symmetric part here, which is gonna be gradient Fe plus gradient Fe dot gradient. Now I put this real so that I don't have to deal with it, and I'll just cancel it directly because it's anti-symmetric. So when I now look at this real part, so I will have to deal with this and this. So let me write first. Now, if I'm gonna take the real part, I actually have to have h minus e part. Well, of course, I'm only writing this as an operator to make things a little short, but, and I will have the n part. Now, what I'm gonna do, like, if you think that as an operator, of course, my Laplacian is a positive operator, so I will get e minus e, and then I will have, now we know that this was less than 1 minus epsilon squared v minus e, exactly. And now you see this is going to be less than epsilon times v minus e. And that's what, and then that will be less than epsilon times delta that we picked over here. So in fact, this delta one with this one.
H is minus of the What happens to the minus?
It's a positive.
Yeah, then we need it to the right. What am I missing? Minus or plus is a positive operator. So I can ignore it. So this is one of the.
Wait, because I did wrong, right? So because it's gonna be like. Yeah, because that's in my mind. Of course, because we need to bound this part, so yeah, sorry. Okay. So, but that's clear that we have that one is this exact thing. Okay, so now second step will be the integration by parts step, and in particular, we are gonna pick what this phi is gonna be. So we will pick phi as into the epsilon n and phi. And now once we pick that, that's actually what we're gonna. Huh? Yeah, okay, so let me put this top data here. And this phi will be again supported in the same way that I define as D data. And C is an eigenfunction. Okay,
Just put phi tilde there where you didn't have it before, but phi tilde has an exponential weight outside. Now you put the exponential weight on phi, and confuse what you mean.
you will see like this is
Where is it tilde now? Where is not?
and now I take my F like a phi tilde, this one, where phi is gonna be again supported in the top, and then C is gonna be in the eigenfunction. Now, once we put it over here, this is what we're gonna have. So I will have delta one e to the and I C output. That's what we want. Will be less than the real part of. Now we just take this and plug it over here. So we will have 2FEN, and I will have 5C. And then when I plug the thing over here, this is gonna cancel. So I will have epsilon times X. Okay, so again, we're gonna.
Just to see where we're going, so in the previous estimate that you made, the point is that you neglected the Laplacian. No, then I'm just. Okay.
Say it again.
No, I just a bit wrong. There was nothing interesting in what I said. So.
Okay.
Yes.
So now we can do some commutation over here because we know that C is the eigenfunction. So this will be actually exactly 5C. And right. And now this is gonna be minus Gaussian. So now actually this the balance of this one is gonna be important because here we're gonna do some integration by parts to put this gradient on the other side. Okay, so if I call this one I. Now I will be equal. I'm just taking these guys and I'm putting on the other side, so I will have 5 e to the 2 f e and 3 5c plus gradient acting on 5 e to the e and e5 5c. So this is what we have. And now I want to bound this by CL2 and gradient out. Now I'm gonna distribute that gradient. And the one of them is gonna cancel actually this fraction of 5 as I calculated. Now let's see again. So now if I distribute here, that so I will have a fraction 5 e to the f epsilon and 5c plus I will have this gradient of 5 squared, which acted on this one, I will and on this side later. And I will have act on this, and it's gonna now act on this one. So I will have that gradient 2 times epsilon and into the epsilon times dot c. So we act on this, and finally we're gonna act on plus I will have gradient 5 e to the e and gradient. Okay, so now this is gonna cancel this one. So once we bound this part, and then because everything now it's compactly supported, you see my phi was already supported in a domain, and its derivatives and are gonna be all supported in a bounded domain. That's why at the end we can take this, we can remove this and actually we can take it to infinity. And don't worry about the rest. So this is what we're gonna bound. We want to bound that 1 e to the n 5cl2. Now, this is gonna be bounded by CL2 norm. This is gonna be bounded by CL2 norm, and this is gonna be also bounded by CL2 norm because everything is compactly supported, and that's okay. So, and this one, we have delta C here, and we also have C on the other side. So in fact, this is what we're gonna have. We're gonna have some CL2, and then I will have, let's say, 1 over epsilon CL2 plus epsilon CL gradient. One over 2 f no. Maybe I should use another one. I'm just estimating this inner product. This what I estimated with some epsilon between 0 and 1. Right. So let me don't use. I use delta 1 epsilon. So that's why, I mean, if I just take this as my reference, so there will be another contact, which is gonna be some, I mean, it's gonna be bounded anyway, that's what I'm gonna say. Let's put C times phi H1. Now I can take n to infinity. And I can actually say that epsilon 5C is bounded. But this domain will be enough. You see that this restricts me in this domain, but that's enough because outside of domain, we already assumed in the statement it was going to be impact. So if you divide in the domain, outside of the domain, the outside domain is going to be already bounded. So this will be actually enough to conclude our statement. Right? Or no. So as Wilhelm said, this is going to be our weighted L2 estimate, but this can be done point-wise. So basically, if though you see this is so this is, I think, why this WKB also doesn't work in the domain 0 to the energy 1 over the energy, because I think in order to prove the point-wise estimate, you need to have differentiability on your potential, and it's so that you can use Polar embedding or elliptic regularity. That's where they're going to be all related to each other. So the second part is going to actually assumes a lot from the potential. So it assumes it's differentiable. Let me check out the statement and then we'll see. Okay. Maybe I can write here. So the point-wise actually estimate requires you to be kind of in LP and K times differentiable and bounded. So and also P will be greater than 1/2 so that you can apply all these elliptic regularities kind of understanding. Then you will have this point-wise estimate that WKB was saying on the corresponding domain. So then it says will be less than e to the I saw actually there are better versions of this one. This is not the optimal optimal requirement for the potential, but I probably they require some more work. But this one is basically only goes like so because of this potential part, you should be able to use the elliptic regularity and keep bounding the sub of this in a wall by its HS norm. And by it's an inductive argument, as I saw. So that's how you'll expand the WKB to higher dimension. Now, if you look at our problem and whatever we just saw in the MATLAB by hand, huh?
I think there are many ways of trying to do that. It's hard. You have all these plane waves. Right?
Yeah.
Into many plane waves, you have a direction, which is the magnitude.
Yeah.
And so that's one way. That is in the discrete spectrum.
Yes.
But what about the
Yes. You are right.
This captures the classically forbidden.
Exactly. Yeah.
Exponentially classically allowed. We don't get any of this kind of the oscillator.
Yes.
That's much more difficult than. But excellent book is what did we needed, I think, is SN, what is it called? It's a gradient studies in AMS, gradient series, gradient the father of gradients, linear partial differential operator systems. He does, the classical Agmon theory also for the continuous one.
Yeah,
Some of the radiation potential distance.
yeah, it sounds, to me, it's almost like. Maybe you need to change your understanding instead of LT to weighted L2 in most of the part when you want to deal with the absolutely continuous spectrum.
Yeah, so you're thinking of limiting absorption principle. Yeah, that's an excellent move. So the resolving is like L2 bounded or the complete spectrum. L2 bounded only in a localized sense. Careful,
Yeah,
not to disrupt the electric.
okay, so in our case, we have. So our potential is. Something like that. And because with sigma square. So this will be the turning point and this will be the allowed region and this will be the forbidden region. So the corresponding picture, if you look at that solution corresponding to this here, right? Then we would expect when sigma square 1r is equal 0, sigma square r minus 1 over r is equal to 0. So when my r is 1 over sigma square, let's put a dash here. So we know here I'm oscillating, and we know that here the picture tells us, I think I was ending up at 1 somewhere. Huh? Go to 0. The picture.
We have 160, but if your solution were not to take your oscillation.
Oh, yeah. So here we have when sigma square minus 1r is positive. And here we have sigma square minus 1r less than 0. So we estimated this part. So we apply the WKB here first. So then our QR will be sigma square r minus 1 over r. Maybe I don't really know if I needed to really write it this way. But then I think I have all the calculation work here. And which will be positive. So that's why my 2, 0 will be 1, and hence qx over w prime x squared will be 2r will be root of we have the calculations here just in case. Okay. So now we're looking over here. So we had this potential that we wanted to be small. In fact, in this case, we calculated together with Wilhelm, and then we figured that it's gonna look like something like 1 over, let me look exactly, 1 over W cube. So that's why it will be integrable in the domain, let's say 1 over sigma squared and we will be fine over there. So our estimate, our approximation to x0, then it's gonna look like 1 over 2r, or I should say, and e to the plus and minus I integral some I'm even gonna put some other here, other slide here, which is gonna be bigger than here. And r sigma squared r minus r over s. Yes. And now this is gonna come exactly what actually I showed in the computer. So my sigma r was what? So we are positive. So my sigma squared r is gonna be positive, right? So this will be r to the 1/2. So this is gonna come 1 over sigma to the 1/2, right? And I will estimate plus and minus I, r star to r. Now, this is gonna be bigger than 1, so I will take sigma out. Then I will have 1 minus 1 over sigma squared x to the 1/2 yes. So if you stand this, it will have 1 over I, and here we have our star to r sigma 1 so I will have derivative 1/2 1 over sigma squared r plus O 1 over sigma 4 r squared. In fact, we will have so it will be sigma r minus r star. And from here I will have 1/2 sigma logarithm r divided by r star. And I will have plus O1 over r, but I need to be careful about the sigma, right? Sigma cube. So I have sigma cube r squared, and I know, let's leave it like that. Plus O 1 over the integral sigma cube r. So that's the behavior at infinity over here. We can convince. so let me don't raise here. And if you look at here, we'll have Mitchell short it over here. So how this WKB, like this F0 approximation come. But over there, the problem is this guy is not, like, it doesn't come as this, let me write that actually.
Before you read, what P did we find to the left of the same point? What was the behavior? What does it, what do the notes say? What behaviors needed we find to the left?
To the left, that's, I was gonna actually write it down in a bit. I can tell you.
One over W. Correct.
We have this, yeah, we have actually the same thing. It's again 1 over W cube, but because we have 0 there.
W cube should be good because.
But that's from 0 to infinity, like
No,
that's,
what did we find to the left? The turning point for the perturbation, for the perturbative potential, for the expression of the approximate. Which
so you are asking F0 or this one?
to the left of the thing.
Yes, to the left, but are you asking our approximation or are you asking V?
Perturbative,
We again find 1 over W cube.
what I said is wrong. I told you that maybe with W going to 0, this grows up. This is totally wrong thinking on my part. Because the W variable, as we go from the turning point to the left, gets large. So again, what will save us is that one of the W cube is integral at infinity. You see, because what does the interval 0 to 1 of the sigma squared get messed?
So the J is changing again, so
So that means that WKB is a good approximation to the left of the turning point. I totally nonsense there.
but
What would kill us if we found the potential 1 over W to the 1/2? That would be a killer because that's not L1.
yeah, I understand what you're saying, but in terms of R, we found it 1 over R to the 3 over 2, right? And if we think about it from 0 to wherever, it's not integrable. How the,
In R, you have the interval 0 to 1 over sigma.
yeah,
And this you transform by the linear concept.
I understand, but
Then you get the action variable W. And in the action, it's just like over there, you say that we found the same behavior 1 over W cubed to the left of the turning point. That means as we go to large values of W, it's integrable and the W could be approximated to the. That's good.
then Nakamura also completely like the Nakamura's paper, even though there he has no singularity, his work is very estimates what we have exactly.
Yes, the Nakamura is in all dimensions, not just one.
Yeah.
This is classical one. Nakamura. Do you want to say a little bit about this very nice formula in Nakamura? No proofs that.
I don't think I can. So if you do the same thing, let me first stay there. So you see we found what is the approximation here. On the other side, the approximation, we have put it over here this morning. It was like e to the negative some constant over sigma. Like this was the approximation. Let me put CR here because it's gonna depend on R and C. I don't remember exactly. And Nakamura says in all dimensions, and but his potential actually covers at infinity hours. So the infinity behavior is like hours, but 0, he doesn't assume any but he assumes the potential is bounded at 0. But still, yeah, yeah. Yeah.
One of the R's in D.
Yeah. So that's what you said, but I just wanted to, before giving the result, I just wanted to mention that. So it estimates this. Sigma to the star. Yeah, some gamma over sigma. So you are in the small. I'm gonna, so it's a cutoff function supported here and here.
It's some kind of smooth. So isn't it? What is this one? It's. So it's probably. It's supported on the negative real, and then vanishes for the positive real. So it's supposed to be a smooth cutoff.
Yeah.
And what does it mean to take an operator H and bounding?
So it says small energy, small sigma, and the domain that we are looking for basically.
F H, let's say the sigma squared is defined by the functional calculus because H is self-adjoint, so we can make sense of that. And this is this remarkable double couplet in phase space. So you take sig x to the left of the turning point at small energy. And then you get exactly this Agmon type decay, e to the minus Agmon distance from 0 to the turning point. Right. And H is minus of 1 plus 1 over R. Basically. Although Nakamura prefers something like one of the Japanese R.
Yes,
Yeah.
so that's why it's just bounded at 0.
Does everybody understand what this means? This says that the probability of finding a state with energy less than sigma squared in the classical forbidden region is exponentially small in the action from 0 to the edge of the exponential to the classical forbidden region. Okay? So it's the Agmon diameter of the classically forbidden region, e to the minus Agmon diameter. Gamma and beta are just some small constant. Okay? A beautiful thing. He cites a paper from 1989, not easy to read, but I can pronounce the authors, I cannot.
Pond, date, and Ebru.
PCP, so breeds, corn, and people. Not easy to read there, unfortunately, a bit formal, but it's paper paper, and it really deals with states supported by double wells or multiple wells. Okay, so enough said.
And just even before the Nakamura, so the point is that here you made all the computation when Q0 is +1, and if you were to go in Q0 is -1, then you have something similar. But now you have e to the minus times that integral, and this is how you get this. And there is no point in tracking R because R is between 0 and 1 over sigma, and then nothing changes there.
No, so that's not what I thought. I just didn't wanna,
Sorry, I didn't understand the question. What did you say?
I don't think,
Well, what happens at the left of the turning point?
You mean in Nakamura?
no, in our
Why
calculation.
do you not care about the R, for example?
No, it's not that I didn't care, I just, write it something and then pass, but if you want, this is what I have in my note as my estimate gives this, if it is correct, that's what I have.
What is that here?
That's
So we have a
this,
fundamental system. Okay, so these are this is the fundamental system right, the right of the zoning.
and this is the left.
Yeah, but then, I have the point. that
Yeah,
We lost R. And by
Yeah, yeah, yeah.
R to the 1/4 is obviously not the correct thing. Right? R to the 1/4 is not the correct behavior of these variables.
yeah,
Something. does go
different,
wrong.
some, okay, then.
Something does go wrong.
I think it should be R.
R,
And it, not the,
I don't know, maybe I did something.
Plain WKB does say that the leading order, no, I mean, you have to take the fourth root of one of our minus sequence. Where I learned some stuff to make it not. Very interesting. Yeah, come with.
Yeah, I think so.
also, I think you can do it, you which like calculate the thing behavior.
What, you did the reaction problem?
Yeah, well.
So to go through the turning point, we use area, I think, direct area. Because you would have to make the transfer from the section. And so area is going to be a normal form. If you also show some complete words.
But it's so that's it.
Huh?
Really, this is it. Like,
This is it, yeah.
Thank you very much.
No problem.